All right, continuing on, working a little more with areas today. So we have a few different things here, a few different shapes, geometric shapes, and we're going to be evaluating integrals and trying to find area. So before I get too far, I'm going to go ahead and just find all the areas. All right, so this one will be 5/2, or 2.5, and that comes from 1/2 times 1 times 5, okay? The next one, this is 1/2 times pi times the radius squared, which would be 2. So that whole thing is 2 pi. So I'm going to go ahead and just write pi here and pi here. So I know it's 2 pi for that whole thing. This would be 1/2 times, oh man, what is that point? So it's worth checking that point out. So in order to find that, let's find the slope of the line. Okay, -1 minus 3 over 5 minus 3. So that's -2. Find the equation of the line. It doesn't matter which point you use. 3 minus 2 times x minus 3. Let's see. I'm trying to find out where that's 0 so I can find the value of that point. So 3 minus 2x plus 6, -2x plus 9. So 2x equals 9. X equals 9/2. So it looks like it was 4.5, but now we know it definitely is 4.5. All right, it's worth checking that so you don't mess up your whole problem. All right, so this is 2.5, 1/2 times 2.5 times a height of 3. So this ends up being what, 15? Okay, 15 halves, right? Or if you like decimals, 15 fourths. Oh man, that would have really messed me up. 15 fourths, or 3.75. All right, and then our last piece here is 1/2 times 1 times 1/2. So that area will be 1/4 or 0.25. All right, for that part. So now we're going to go ahead and evaluate our first one. We're trying to evaluate from -7, that integral from -7 to 0. So that's going the correct way from left to right. So from -7 all the way to 0, that's going to be -2.5 because it's underneath the x-axis plus pi. That's it, okay? Does this represent the area of the region? No, okay? The area would be equal to, or the area could be approximated by 2.5 plus pi. All right. For part B now, we are trying to evaluate the integral from 2 to 5, right, of f of x dx. And that one, it's a good thing we already did all these areas, right? We have 3.75 minus 0.25. And if you want to write that, that would just be 3.5. And does that represent the area? No, in that case, again, the area could be approximated by 3.75 plus 0.25. Remember, the integral just represents the net accumulation over this. All right, the area, and again, this doesn't represent the area of the region because we have portions of the graph that are below the x-axis. All right. So let's move on to this. These are a bunch of properties of integrals, and we're going to see these things happen the more problems you start doing. All right, and you could read through these yourself. If we're just going to A, we're not going anywhere, okay? If we're going to the next value, that's why that's 0. We have already seen this example that if you go the opposite way, you can just put a negative in the front. The constant, that's like our problem where we did before, where it's just a rectangle. All right, so you're just doing like the constant value multiplied by b minus a. Here you can add or subtract. If two functions are being added or subtracted, you can add and subtract those integrals. The constant, just like with derivatives, you could pull it out in the front. All right, and then this part, you can break anything apart. And I showed you a few examples of that before. If you're going from 0 to 5, you can go there any way you want, okay? So you could go from 0 to 2, maybe this will be easier, and then 2 to 5. All right, so that's one of the properties. Let's use that to get to our answer here. Well, we're trying to rewrite this another way. All right, so I am going to go ahead and just first write it as two different integrals. I don't know what I need to figure out yet, so I'm not going to do too much, okay? Then what I can do is pull that 3 out of the front. All right, and I'll evaluate this in a minute. But now, do we know what the integral from 8 to 10 is? We don't, but what we do know is this. We could write it as 8 to 0 plus 0 to 10. We have both of those. All right, there's a couple ways of doing this problem. This is just one. And we still have that other part from 8 to 10 of 2 dx. Great. All right, so we don't know 8 to 0, but we do know 0 to 8. And remember, that's just going to be the opposite of that. So 3 times negative 12 plus, from 0 to 10 is 17. Okay, plus this part, that's just 2 times 10 minus 8. So we have 3 times 5 plus 2 times 2, 15 plus 4, looks like 19 is the value of that integral. All right, we have 2 more problems to go, I think. 14 is a good one, but we got to start with 13 first. All right, using the area of the region to help evaluate it. So at this point, I'm positive that this wouldn't be easy to do, trying to find the antiderivative. All right, and so sometimes when you can't easily do that, maybe it would be a good idea to draw a picture. And hopefully that you remember this from last year, or maybe in the beginning of the year. A function like this is undefined at 3 because there's a hole there. All right, so another way of writing this, x plus 3, x minus 3. This part cancels out. So we can use this function, negative x minus 3, when x isn't equal to 3 because there's a hole there. All right, and the hole, if we take the limit of negative x minus 3 as x approaches 3, we could figure out that would be negative 6. All right, this is all stuff that we've done before. Hopefully you remember some of it. So we could draw this graph, negative x minus 3. But we have a hole at the point 3, negative 6. All right, so we're trying to find the area from negative 5 all the way to 6. So we need this part here. And this part. And our function's not continuous, but that's not going to stop us here from finding this out. And it looks like we just have 2 triangles, so this isn't going to be so bad. All right, so the area of this part is just going to be 1/2 times 2 times my height is 2, so the area is just going to be 2 for that part. Okay, right here, 1/2 times, what is that, 9 times 9 equals 81 over 2, or if you want to write it as 40.5, either way. Now we can evaluate this integral. 9 minus x squared over x minus 3 dx. That's simply going to be equal to 2, positive 2, right, minus negative 40.5, or I mean minus, not negative, minus 40.5, and if you want to write it as a number, negative 38.5. It's a good idea to check this on your calculator. All right, and then I know it doesn't ask this, but if you were asked to approximate the area, then that would just be 2 plus 40.5, or 42.5. All right, last problem. This is a great graph. It'll help you kind of break these down. The graph's already on here for you. So if we know that this is 2, all right, the area from 0 to pi of sine of x equals 2. And we also know that sine is an odd function. It's symmetrical about the origin, so we know that one's 2. All right, and so on and so forth. Okay, if we kept drawing these parts here, this would be 2, this would be 2. So let's evaluate some of these. All right, from pi, which would be here, all the way to 2 pi. If we integrate that, we're going to get -2 because it's below the x-axis. Okay, to go from 0 to 2 pi, we would have 2, and then we would have -2. So this one's just 0. Okay, the area like cancels out the other area. Let's see, now if we look from 1/2 pi to pi, this one is going to be, I'm sorry, we read that backwards. It's from pi to 1/2 pi. We're going backwards. We're going in the opposite direction here. So this one ends up being -1. All right, this, we can use our properties to break this apart. Okay, 2 times pi minus 0, that's just 2 pi, plus the integral from 0 to pi, that's just pi. Oh, I mean, that's just 1. I don't know why I wrote pi. 1. So this one is just 2 pi plus 1. Okay, and a letter E, 2 times, we could bring that, remember, using our properties, we could bring it right out in front. So this will be 2 times 2, or in this case, 4. Still not too bad. All right, we'll try a couple. There's a few more left. Ah, man, this one, let's see. Do you remember? This moves the function to the right 2 units. Our original one started at 0 and went to pi, but look, this moved it to the right 2. This one moved it to the right 2, so this is just our normal area function. Okay, it's the same exact thing as 0 to pi of sine of x dx, which is just 2. This one may be a little bit less obvious, okay? Remember, if you divide by a number or multiply by a fraction, okay, on the inside, it's a stretch by a factor of 2. And so normally it goes like this in 2 pi, but in this case it goes 4 pi. And so it kind of stretches out that same piece, but this stretch actually preserves the area. So the area is going to be the same, and that's a little bit intuitive. We don't have the mathematical background, the analytical background yet to back that up. All right, -pi to pi. Let's take a look at our graph here. This would be -pi. So if we go from -pi, that'd be -2 to 0. And then 0 to pi, that's going to be +2. So this one ends up being 0. Now, this time we have cosine of x. Whoa. Let's see, you know what that graph looks like, hopefully. All right, it does not have the same, it's not an odd function. Okay, this time it's an even function. So this is going to be the same area, but it's going to be just a little bit different. So I want you to go ahead and do I and J and plug them right into your whisk. So the first one shouldn't be too bad, and the second one really shouldn't be that bad either. All right, have a great